Hello there, math peeps. This is Mrs. Marshall again, here with day 4, complex zeros. So to begin, to factor a polynomial with complex solutions and zeros completely, keyword here being completely, you are going to write what we call linear factorization of the polynomial. So here's our first example. We want to write the linear factorization of the factors. So right now, the way that it is factored as much as we can, but the linear factorization is where x is a linear variable. Well, in other words, there is no power, or the power is 1. So for the first one, x plus 2, that's linear. But for the second one, x squared minus 3, that is quadratic. And so that's a no-no. And what we need to do is solve for x when we set it equal to 0. And so add 3 to both sides. And then x squared equals 3. Take the square root of both sides. So x equals plus or minus, because remember, a plus or minus attaches to every square root. And so x equals plus or minus square root of 3. Now the final thing before the final answer is what are all of your zeros. So therefore, that's what those three dots represent. X equals -2 for that one, and x equals positive square root of 3 and x equals negative square root of 3 are the zeros. And now we just need to write the linear factorization. So our linear factorization, and I'm going to spell it out, linear factorization is, well, what the factors are for each zero. So for the x equals -2, that's going to be x plus 2. And that again is for x equals -2. And then for the x equals the square root of 3, that's x minus square root of 3. Because it always turns opposite. And for the x equals negative square root of 3, that is x plus square root of 3. And that is our complete linear factorization. You may have seen this already. Your teacher may have shown you from the day 3 practice, but I wanted to show you officially in a notes. So let's move on to the next thing. If z is a complex zero. All right, let's refresh our memory on complex zeros. Remember, that is a plus bi. And then what it is saying is if a plus bi, which is a complex zero, is a 0, then the conjugate, which is a minus bi, is also a 0. So what you know, in other words, are 2 zeros off gate whenever you have a complex zero. You know the complex zero and the conjugate. So let's do an example. P of x equals x cubed minus 3x squared plus x minus 3. And it has a 0 at I. That's a complex zero. Let's see what the rest of the zeros are and write the linear factorization. So from the beginning, off gates, I is a 0. So since I is a 0, negative I is a 0 too. And so we now have 2 things that we can do synthetic division with, starting with thing number 1, I. So our synthetic division, take all of our coefficients and list them there, bring down the 1, and now let's multiply. I times 1 is I. And now we have to add these. Well, you can't technically add that, so you just have to leave it as a sum, -3 plus I. And then multiply, so that's -3I plus I squared. But remember, I squared equals -1. So we want to rewrite this to be -3I minus 1. And then remember what I told y'all last video, real with real, fake with fake, or rather imaginary with imaginary. -3I has no other imaginary number to go with, and the ones cancel out. And so our final answer is -3I. Multiply that with I, and that is -3I squared. But ding, 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 we have an I squared again. And this bad boy ends up equaling positive 3. And so when we cancel that out, negative 3 plus 3 is 0, which is what we knew we should have gotten since that's the last terms, and plus I is a 0. So that means there's no remainder. Now we have to keep on going. This time, divide by negative I. And bring this down. And negative I times 1 is negative I. Real with real, imaginary with imaginary. So that is negative 3. And look at there. They cancel out. And then negative 3 times negative I is 3I. And look at there. They cancel out again. And that is 0. And so since we don't have a calculator, we don't know what other values to divide by. So now we have to stop. We are literally done. And we just need to write our zeros. And then we can write our linear factorization. So the zeros so far are from the I, that is x equals I. From the negative I, that is x equals negative I. And from this 1 minus 3, or the negative 3, technically it's x minus 3. We set it equal to 0 so we can figure out what x actually equals, and x equals 3. So those are our zeros. But what is the question asking us? The question asks us to find the other zeros. So I don't want the I one, I want the other ones. And to do the linear factorization. Right, so our other zeros are all other zeros are x equals negative I, because it's a conjugate, and let's not put a comma, let's put an and, x equals 3. Now let's write that linear factorization. Okay, we're going to abbreviate that to LF. The linear factorization is x minus I. Where did that come from? Oh, that's because x equals I is still a 0. So we have to incorporate that one. Then x plus I, because x equals negative I is also a 0. And x minus 3, because x equals 3 is also a 0. And this is our final answer. Ta-da! Look at us. Go us. Next example. Example number 2. This time, I don't give you any zeros at all. You have to find all the zeros from the beginning with me not giving you anything. And you still want to write the linear factorization. All right, so the question is, where do you start? Well, let's start with factoring. We don't have any numbers that we can divide by, so we just got to factor this thing. And the question is, how? Quadratic, GCF, yes, GCF. And of course, you know it equals 0. So this is 3x, that's our GCF. X to the 4th is what's left, plus 8x squared plus 16. And all of that equals 0. And now, how do you solve it moving forward? Your teacher may have done this in class with a previous one, but when you have a 4th degree polynomial in this form, polynomial in the form x to the 4th plus x squared plus c, and this is in no way, shape, or form officially the I guess the terminology or the actual equation for this, but ultimately you have to have a 4th degree, a 2nd degree, and then a linear, or not a linear, a constant term. Then you are going to factor like a quadratic. And we're going to factor like a quadratic trinomial specifically. And the way I factor quadratic trinomials is doing headphones. Some of your teachers may do that as well. However you factor, maybe with big X, factor it. What times what is 16 but adds to equal 8? 4. And now we write our factors. 3x comes down. This is now x squared plus 4, because we have to make sure we take into account that we need 2 sets of x squareds to get x to the 4th. And we have x squared plus 4 as well. And now we can write our zeros and figure out what those are so that we can, one, answer the question and then write our linear factorization. So 3x equals 0, divide by 3, so x equals 0 still. Okay, x squared plus 4 equals 0, so x squared equals negative 4. But then, of course, take the square root of both sides. And x equals plus or minus, don't forget the plus or minus, 2i. And then this one, oh, guess what? It's exactly the same. X squared plus 4 equals 0. And so we do all the work and we get x equals plus or minus 2i still. And so those are all of our zeros. Let's write our final answer. All zeros are x equals 0, x equals plus or minus 2i, and x equals plus or minus 2i. Yes, we have plus or minus 2i once, but this is letting us know that this is I don't want to circle it yet. This is a bounce, or in other words, we have a 0 that's a multiplicity of 2. So now let's write our factorization with this in mind. I should abbreviate that LF again. All right, so for the x equals 0, we write that as a factor, and it's literally just x. There's no plus or minus anything because that's 0. And then for the x equals plus 2i, let's do that one step at a time. That is technically going to be x minus 2i squared, and that is for x equals positive 2i. And I'm squaring it because I end up with 2 of them. So that's the same as having x minus 2i times, or rather plus, and x plus 2i, because I have it twice. And our last factor is x plus 2i squared. Why? Because it's of the same situation. I have x equals negative 2i, because remember it turns opposite. I have it twice. And so that is having x plus 2i twice as well. And this is our linear factorization. The squared can be of the factor, but it cannot be of the variable. So you cannot have x squared, but you can have the factored squared. And you are still in compliance with a linear factorization. All right, so our next example. Find a polynomial this time of p of x with degree 3 and zeros at 1/2 and 3 minus I. Ooh, so we got to find a polynomial this time. So let's start with what zeros we know. We know that x equals 1/2. And that is a multiplicity of 1. Why? Because it didn't say it was any other multiplicity. And we have x equals 3 minus I with multiplicity of 1. No other multiplicity was stated. But remember, 3 plus I is automatically a 0, 2. So we have that x equals 3 plus I as a 0 with multiplicity of 1 as well. And now let's write our factors so that we can multiply this bad boy together so we can get the polynomial with the degree of 3. So this is x minus 1/2 times x minus 3 plus 1, not plus 1, plus I. And sorry, my pen keeps going in and out. And then our last one is x minus 3 minus I. Now remember, where did I get these from? X equals positive 1/2, so it has to turn opposite. Versus this one, x equals 3 minus I, so both things will literally turn opposite. So we have to make sure that we know this 3 will turn into a negative 3, and this I will turn into a positive I. And the same situation for this one. X equals 3 minus I, well, plus I to begin with. So it has to turn opposite. This 3 is now a negative 3, and this I is now a negative I. All right, now let's multiply. We got to multiply all of this together, and you can decide how you want to multiply. I polled my class today, actually, and they said they like doing the shortcut, like they know how to FOIL. So I was like, yes, y'all better know how to FOIL. But in case you don't, we're gonna just multiply this out. So I'm gonna do these two terms first, and I kind of want to get rid of these little highlights. It's kind of messing me up. Let's get rid of those. All right, so let's multiply those two first. X minus 3 plus I going down the side, and then x minus 3 minus I going across the top. Now again, it doesn't matter where you put what. Like if you put what I put on the side on the top, that's totally fine. All right, now let's multiply. X times x, x squared, negative 3x, just going straight down. And then xi or ix, it really does not matter. There's no square root. And then negative 3x and negative xi. And the middle, negative 3 is positive 9 and negative 3i. And then the end, negative I times negative 3 is positive 3i. And negative I times positive I is negative I squared. All right, let's look and see if we can figure out some things like what in here do we actually need in terms of our polynomial. Well, step one, we have I squared. And don't forget that this is the same thing as negative 1, or technically negative times negative 1, because I squared is negative 1. So that is positive 1. Anything else we can get rid of? Let's see. X squared, that doesn't have a partner. So negative 3x and negative 3x, those go together. But then, the negative xi and these two cancel out. The positive 3i and the negative 3i. Oh, the imaginary numbers cancel out. And then this 9 and this 1, they go together because they are whole numbers. So now we can write it in a straight line. X squared minus 3x minus 3x plus 9 plus 1. And we can simplify. Let's make this x look a little more like an x. And we end up with x squared minus 6x plus 10. That looks more like normal because having a polynomial with i's in it, like what? We've never seen that before. Now we have to make sure we understand that that goes over here. So x minus 1/2 times now x squared minus 6x plus 10. And now we have to multiply that as well. We have the endurance. We can do it. X minus 1/2 is going to be on the side. And then our long top part is x squared minus 6x plus 10. Again, you can multiply this with the FOIL method if you have it. But the majority of us, I don't know, I guess we like the box. Well, I'm just doing the box. So x to the third. Oh, there's our third degree finally. Now x squared and negative 1/2 is, let's go back for a moment. Instead of multiplying by x minus 1/2, let's change that. Let's multiply by, instead, we divide that 2 in the front, but slide or divide. So 2x minus 1, because that is the exact same thing. So this now needs to be what we are going to divide by or multiply by. And so over here to the side, let's change that. Instead of x and negative 1/2, let's do 2x and negative 1. It will make our answers come out so much better because we won't have to deal with a fraction. Who likes dealing with fractions? So our first answer is going to change as well. So instead of it just being x cubed, it's 2x cubed. And x squared and negative 1 is negative x squared. This is negative 12x squared. This is positive 6x. Positive 20x, and negative 10. And now we want to combine like terms. Nothing's combined with the x cubed, but these x squareds are a match, and these x's are a match. And we write our final answer. You can actually combine them inside of the box, or technically mentally, and get 2x cubed. Well, this negative 12x and negative x squared is negative 13x squared. So that's what that equals. Plus 26x, that's what that equals. And then minus 10, because there's nothing to combine with that. And lo and behold, we are finished. So P of x equals 2x cubed minus 13x squared plus 26x minus 10. And that is our third degree polynomial with those two zeros. Technically those three, because 3 plus I, the conjugate, is a 0 as well. All right, guys, the last problem. Woo! Solving polynomial inequalities. Oh, inequalities, how do they work? Well, this definitely calculated inactive. And what you need to know is it has to be greater than, less than, greater than equal to, or less than or equal to 0. Has to be to 0. And the next thing, oh, where did it go? There it goes, is our picture. The picture of this thing is very simple to hopefully understand. So it's talking about everything on top or greater than y equals 0. And so everything greater than, which you know what the greater than sign is, or greater than or equal to. Oh, let's write the greater than or equal to part. Greater than or equal to. And it has to be 0. So both of these are then 0. And that's everything that's on top. So you're trying to tell me what part of the graph is on top. And then we have the bottom. Everything down here on the bottom is less than or less than or equal to. So less than, and you know what the less than sign looks like. It looks like this, or less than or equal to. And that's right there. And again, it has to be to 0. And that is literally what parts of the graph are below the x-axis or below y equals 0. So we want to write an answer in interval notation. Write an answer in interval notation. And that's ultimately the end goal. Our example, let's go ahead and do the last example. And here's our inequality. So the first step is we need to make sure that it's greater than, less than, equal to the inequality or the value 0. And so we double check that and check, ding, 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 we are good to go. So I'm gonna actually do that in green because this is the greater than or equal to sign than 0. And so we're gonna be looking for the part that's on top, which I highlighted in green as well. So let's figure out what's the first step after that, though. We got to graph this inequality. We're literally going to graph it like a regular old equality. So we need to figure out what are the zeros. 5x squared, and I'm not going to start with parentheses. We'll put them in just a minute. So we're going to pretend like the 0 isn't there, and we're just going to solve it like a regular inequality or a regular equality. But I'm going to solve this with grouping. Why? Because I can't factor with GCF. I can't factor trinomials. I can't do a lot of things. But what I can do is take this x squared out of this first term, honey. X plus 5 is what that ends up equaling. Minus 4, you take that bad boy out, and that's x plus 5 again. Up, and look at there. We have a GCF. This x plus 5 and this x plus 5 are the same. So we pull that out, x plus 5 in the front, and x squared minus 4, I put that in the back. Now, it doesn't matter. Can you put it the opposite way? Yeah, definitely. You can do what you like, as long as it's right. And x plus 5 equals 0. And x squared minus 4 equals 0, because we're trying to find the zeros. And so x equals negative 5. And this one, x squared equals 4. And so x equals, you take the square root of both sides, plus or minus 2. No imaginary numbers are a part of this, guys. We're just looking at an inequality, like switched it up real quick. Now, let's go back to regular numbers, real numbers, and let's do this inequality. So we have two real number zeros. Technically 3, because you have plus or minus 2, no I. And so now we need to identify a couple more things. Our degree is 3, so it's not even, it's positive. Positive. So that means it is a line going up. That kind of gives us our end behavior. Zeros, the zeros are x equals negative 5 with a multiplicity of 1. I only have it one time. X equals positive 2 with a multiplicity of 1. And x equals negative 2 with a multiplicity of 1. And what is our y-intercept? Because we're graphing this from scratch, so backing it on up, what was our y-intercept? Well, because it's in standard form to begin with, our y-intercept is 0, negative 20. And now we can graph this. So go to negative 2, put a dot, go to negative 5, put a dot, and go to positive 2, put a dot. Our y-intercept is way down here, so I'm just extend the line a little bit, and that is going to be negative 20, give or take. Probably give a whole lot. So we want our picture to go in this direction. So we start from the bottom, and if it's a positive or a negative 1, not a negative, a multiplicity of 1, it goes through. Go up some, I don't care how far up you go, it goes through again, but it's got to go all the way down to your y-intercept, and then this is going to go through again because all of these have an odd multiplicity. And that is our picture. Now the question is, what's the answer to this actual question? We got to write the answer in interval notation. What parts of the graph are greater than 0 above? So we take a look at this section of the graph. What sections are in the green? So the sections in the green are from here to here. Let's see if I can make that a little darker. All right. And from here to here. It's a straight line. So we just need to write that as an inequality, though. Our inequality answer is therefore, we know that this is negative 5, that's negative 2, and that's positive 2, and this is infinity. So this graph is greater than 0 from negative 5, and it has a bracket because it can be equal to negative 2, union with positive 2 to infinity. And infinity never gets a bracket because you can't touch that number. It goes forever. And that is our final answer. All right, so this was a short video, I hope. Yes. Please make sure that you copy the notes and listen to the notes. And I will see y'all next unit. Marshall, out.